Chapter 4. Robots and Rationality. In his 1962 book, The Structure of Scientific Revolutions, the philosopher Thomas Kuhn argued that, as scientific understanding advances, there will be times when established scientific orthodoxy can no longer hold up under the strain of manifest failures. At such times of crisis, he argued, a new orthodoxy will emerge and replace the established order. The scientific paradigm will change. By the late 1980s, the boom days of expert systems were over, and another AI crisis was looming. Once again, the AI community was criticized for overselling ideas, promising too much, and delivering too little. This time, the paradigm being questioned was not just the knowledge is power doctrine that had driven the expert systems boom, but the basic assumptions that had underpinned AI since the 1950s, symbolic AI in particular. The fiercest critics of AI in the late 1980s, though, were not outsiders, but came from within the field itself. The most eloquent and influential critic of the prevailing AI paradigm was the roboticist Rodney Brooks, who was born in Australia in 1954. Brooks's main interest was in building robots that could carry out useful tasks in the real world. Throughout the early 1980s, he began to be frustrated with the then prevailing idea that the key to building such robots was to encode knowledge about the world in a form that could be used by the robot as the basis for reasoning and decision-making. He took up a faculty position at MIT in the mid-1980s and began his campaign to rethink AI at its most fundamental level. The Brooksian Revolution. To understand Brooks's arguments, it is helpful to return to the blocks world. Recall that the blocks world is a simulated domain consisting of a tabletop on which are stacked a number of different objects. The task is to rearrange the objects in certain specified ways. At first sight, the blocks world seems perfectly reasonable as a proving ground for AI techniques. It sounds like a warehouse environment, and I dare say exactly this point has been made in many grant proposals over the years. But for Brooks and those that came to adopt his ideas, the blocks world was bogus, for the simple reason that it is simulated, and the simulation glosses over everything that would be difficult about a task like arranging blocks in the real world. A system that can solve problems in the blocks world, however smart it might appear to be, would be of no value in a warehouse, because the real difficulty in the physical world comes from dealing with issues like perception, which are completely ignored in the blocks world. It became a symbol of all that was wrong and intellectually bankrupt about the AI orthodoxy of the 1970s and 1980s. This did not stop research into the blocks world, however. You can still regularly find research papers using it to the present day. I confess to have written some myself. Brooks had become convinced that meaningful progress in AI could only be achieved with systems that were situated in the real world. That is, systems that were directly in some environment, perceiving it and acting upon it. He argued that intelligent behavior can be generated without explicit knowledge and reasoning of the kind promoted by knowledge-based AI in general and logic-based AI in particular, and he suggested instead that intelligence is an emergent property that arises from the interaction of an entity in its environment. The point here is that when we contemplate human intelligence, we tend to focus on its more glamorous and tangible aspects, reasoning, for example, or problem-solving, or playing chess. Reasoning and problem-solving might have a role in intelligent behavior, but Brooks and others argued that they were not the right starting point from which to build AI. Interestingly, these higher aspects of human intelligence are handled by a part of the brain called the neocortex, and the record of human evolution tells us that this part of the brain evolved only relatively recently. Reasoning and problem-solving are quite new capabilities for people. Our ancestors coped without them for most of evolutionary history. Brooks also took issue with the divide-and-conquer assumption that had underpinned AI since its earliest days, The idea that progress in AI research could be made by decomposing intelligent behavior into its constituent components, reasoning, learning, perception, with no attempt to consider how these components worked together. Finally, he pointed out the naivety of ignoring the issue of computational effort. In particular, he took issue with the idea that all intelligent activities must be reduced to ones such as logical reasoning, which are computationally expensive. As a student working on AI in the late 1980s, it seemed like Brooks was challenging everything I thought I knew about my field. It felt like heresy. In 1991, a young colleague returning from a large AI conference in Australia told me, wide-eyed with excitement, about a shouting match that had developed between PhD students from Stanford, McCarthy's home institute, and MIT, Brooks's. On one side, there was established tradition, logic, knowledge representation, and reasoning. On the other, the outspoken disrespectful adherents of a new AI movement not just turning their backs on hallowed tradition, but loudly ridiculing it. While Brooks was probably the highest profile advocate of the new direction, he was by no means alone. Many other researchers were reaching similar conclusions, and while they did not necessarily agree on the smaller details, there were a number of commonly recurring themes in their different approaches. The most important was the idea that knowledge and reasoning were deposed from their role at the heart of AI. McCarthy's vision of an AI system that maintained a central symbolic logical model of its environment, as in Figure 5, around which all the activities of intelligence orbited, was firmly rejected. Some moderate voices argued that reasoning and representation still had a role to play, although perhaps not a leading role, but more extreme voices rejected them completely. It is worth exploring this point in a little more detail. Remember that the McCarthy view of logical AI assumes that an AI system will continually follow a particular loop, perceiving its environment, reasoning about what to do, and then acting. But in a system that operates in this way, the system is decoupled from the environment. Take a second to stop listening to this audiobook and look around. You may be in an airport departure lounge, a coffee shop, on a train, in your home, or lying by a river in the sunshine. As you look around, you are not disconnected from your environment and the changes that the environment is undergoing. You are in the moment. Your perception and your actions are embedded within and in tune with your environment. The problem is, the knowledge-based approach doesn't seem to reflect this. Knowledge-based AI assumes that an intelligent system operates through a continual perceive-reason-act loop, processing and interpreting the data it receives from its sensors, using this perceptual information to update its beliefs, reasoning about what to do, performing the action it then selects, and starting its decision loop again. But in this way, an AI system is inherently decoupled from its environment. In particular, if the environment changes after it has been observed, then it will make no difference to our knowledge-based intelligent system, which will stubbornly continue as though nothing had changed. You and I are not like that. For these reasons, another key theme at the time was the idea that there should be a close-coupled relationship between the situation that the system finds itself in and the behavior that it exhibits. Behavioral AI. If Brooks had been just another critic of AI, it is unlikely that his ideas would have gained much traction. After all, by the mid-1980s, the AI community was accustomed to ignoring its critics and carrying on regardless. What raised Brooks's critiques from being yet another Dreyfus-style attack was that he convincingly articulated an alternative paradigm and demonstrated it with some impressive systems in the decades that followed. The new paradigm for AI became known as behavioral AI because, as we shall see, it emphasized the role of the specific individual behaviors that contribute to the overall operation of an intelligent system. The particular approach adopted by Brooks was called the subsumption architecture, and of all the approaches from the period, This seems to have had the most lasting impact. So, let's see how the subsumption architecture can be used to build a modest but useful robotic application. A vacuum cleaning robot. Brooks was a founder of the company iRobot, manufacturer of the popular Roomba robot vacuum cleaners, the design of which was based on his work. Our robot will be required to travel around a building, avoiding obstacles and vacuuming when it detects dirt. When the robot has a low battery, or its dirt container is full, we want it to return to its docking station and shut down. The basic methodology for the subsumption architecture requires identifying the individual component behaviors that are required for the robot. We then start to build our robot by getting it to exhibit one of the behaviors and then progressively add further behaviors. The key challenge is to think about how these behaviors are interrelated and to organize them in such a way that the robot is exhibiting the right behavior at the right time. This typically requires experimenting with the robot extensively to ensure that the behaviors are organized in the right way. Our vacuum cleaning robot requires 6 behaviors. Avoid obstacles. If I detect an obstacle, then change direction, choosing a new direction at random. Shut down. If I am at the docking station and have a low battery, then shut down. Empty dirt. If I am at the docking station and am carrying dirt, then empty dirt container. Head to dock. If the battery is low or dirt container is full, then head to docking station. Vacuum. If I detect dirt at the current location, then switch on vacuum. Walk randomly. Choose a direction at random and move in that direction. The next challenge is to organize these behaviors. For this, Brooks suggested using what he called a subsumption hierarchy. See Figure 6 on the attached PDF. The subsumption hierarchy determines the precedence for behaviors. Those that appear lower in the hierarchy take precedence over those that appear further up. Thus, obstacle avoidance is the highest priority behavior. The robot will always avoid obstacles if it ever encounters one. It is not difficult to see how these behaviors, organized into the hierarchy in Figure 6, will solve the problem. The robot will search for dirt and vacuum when it finds dirt, as long as it is not low on power or the dirt container is full. It will return to its docking station if the battery is low or the dirt container is full. Although the behaviors in our vacuum cleaning robot look like rules, they are in fact much simpler. To implement them within a robot requires nothing like as much effort as logical reasoning. In fact, they can be directly implemented in the form of simple electrical circuits, and as a consequence, our robot will react to changing sensor data very quickly. It will be in tune with its environment. In the decades that followed, Brooks built a string of influential robots, using the subsumption architecture as the basic development framework. His Genghis robot, for example, which now resides in the Smithsonian National Air and Space Museum, used 57 behaviors arranged into a subsumption architecture to control a 6-legged mobile robot. It would have been ludicrously hard to build Genghis using knowledge-based AI techniques if it had been possible at all. These developments propelled robotics back into the mainstream of AI, after decades on the sidelines. Agent-based AI. At the beginning of the 1990s, I met one of the chief protagonists of the behavioral AI revolution, then something of a hero of mine. I was curious about what he really thought about the AI technologies that he was loudly rejecting: knowledge representation and reasoning, problem-solving and planning. Did he really believe these had no place at all in the future of AI? Of course not, he answered. But I won't make a name for myself agreeing with the status quo. It was a depressing answer, although with hindsight, he was probably just trying to impress a naive young graduate student. But whether this professor really believed in what he was doing, others certainly did, and behavioral AI quickly became as mired in dogma as the traditions that had gone before. And before long, it began to be clear that while behavioral AI had raised important questions about the assumptions upon which AI was based, it too had severe limitations. The problem was it didn't scale. If all we want to do is to build a robot to vacuum an apartment, then behavioral AI is all we need. A vacuum-cleaning robot doesn't need to reason or be able to converse in English or solve complex problems. Because it doesn't need to do those things, we can build autonomous robot vacuum cleaners using the subsumption architecture or something like it. There were lots of similar approaches at the time, and we will get a beautifully efficient solution. But while behavioral AI was very successful for some problems, mainly robotics, it provided no silver bullet for AI. It is hard to design behavioral systems with more than just a few behaviors, because understanding the possible interactions between behaviors becomes very difficult. Building systems using behavioral approaches was a black art. The only way to really know whether such a system was going to work was to try it out, and this was time-consuming, costly, and unpredictable. Brooks was surely correct to point out that capabilities such as knowledge representation and reasoning are not the right foundations upon which to build intelligent behavior. And his robots demonstrated what could be achieved with purely behavioral approaches. But the dogmatic insistence that reasoning and knowledge representation have no role to play was, I think, a misstep. There are situations that naturally call for reasoning, whether strictly logical or otherwise, and to try to deny this makes no more sense than trying to build a vacuum-cleaning robot that decides what to do by logical deduction. While some proponents of the new AI took a hard-line view, anything like logical representation and reasoning were strictly verboten, others adopted a more moderate line, and it is this more moderate line that seems to have prevailed through to the present day. Moderates accepted the key lessons of behavioral AI, but argued that the right solution was a combination of behavioral and reasoning approaches. A new direction for AI began to emerge, which took on board the key lessons of Brooks while at the same time embracing what had previously proved to be successful in AI's reasoning and representation heritage. Once again, the focus of activity in AI began to change, away from disembodied AI systems like expert systems and logical reasoners, toward building agents. An agent was intended to be an AI system that was complete, in the sense that it was a self-contained, autonomous entity, situated in some environment and carrying out some specific task on behalf of a user. An agent was supposed to provide a complete, integrated set of capabilities, rather than just some isolated, disembodied capability like logical reasoning. By focusing on building complete intelligent agents rather than just the components of intelligence, it was hoped that AI could avoid the fallacy that so irked Brooks, the idea that AI can succeed by separating out the components of intelligent behavior, reasoning, learning, and so on, and developing these in isolation from one another. The agent-based view of AI was directly influenced by behavioral AI, but softened the message. The movement began to emerge in the early 1990s. It took the community a while to agree on what they were really talking about when they talked about agents, but by the mid-1990s, a consensus emerged that agents had to have three important capabilities. Firstly, they had to be reactive. They had to be attuned to their environment and able to adapt their behavior appropriately when changes in the environment demanded it. Secondly, they had to be proactive, capable of systematically working to achieve their given task on behalf of their user. Finally, agents were social, capable of working with other agents when required. The golden age of AI had emphasized proactive behavior, planning and problem-solving, while behavioral AI had emphasized the importance of being reactive, embodied in and attuned to the environment. Agent-based AI demanded both, and in addition, threw something new into the mix, the idea that agents would have to work with other agents, and for this, they would need social skills. The ability not just to communicate, but to cooperate, coordinate, and negotiate with other agents in the furtherance of their tasks. It was this latter consideration, that agents need to be social, that marked out the agent-based AI paradigm from those that had preceded it. With hindsight, it seems somewhat strange that it took AI so long to start seriously thinking about how AI systems might interact with each other and what issues would arise when they did so. Homer, a complete agent. My favorite example of an agent from this time was Homer, a simulated robot submarine which existed in a two-dimensional sea world. Homer was given tasks to accomplish in the sea world, which typically related to collecting packages and moving them from one location to another. Homer is clearly a spiritual descendant of Sherdlu, and shared with Sherdlu one of its key limitations. It was only a simulation. But it was considerably more sophisticated. Homer took instructions from a user within a limited subset of English with about an 800-word vocabulary. Homer could plan how to achieve its instructions and could then carry out its plans, adapting them as circumstances required. To get a feel for Homer's capabilities, let's look at some dialogues with it. The first concerns a floating log that Homer could see. "What is in front of you?" Homer's response, "A log." "Do you own the log?" Homer's response, "No, I don't." "The log belongs to you." Homer's response, "Oh," used by Homer to indicate it has been told something it didn't know previously. "Turn away from your log." Homer's response, "Okay, I am turning." Log is moved by the user. "Turn around." Homer's response, "Okay, I'm turning." "I've lost the log." This dialogue demonstrates some simple but important common-sense reasoning. Homer remembered about the log, expected to see the log when it turned around, and was surprised when it discovered that the log had disappeared. The next scenario starts with Homer waiting at a pier, which has a package on it. Homer's task was to collect the package and deliver it to a barge. "Drop the package at the barge next Saturday at 9 p.m. Homer's response, "Okay." Homer generates plan. "Are you going to the pier next Saturday?" Homer's response, "Yes." "Why are you going to go to the pier?" Homer's response, "I'll go to the pier in order to pick up the package." "What time are you going to pick it up?" Homer's response, 8:56 p.m. "Where will the package be next Sunday?" Homer's response, "At the barge." "Will the package be at the pier a week from now?" Homer's response, "No." Here, we see Homer demonstrating some common-sense understanding of time and how its actions affect its environment. That after it has dropped off the package at the barge, the package will no longer be at the pier. It also demonstrates an understanding that its own plans will take time to accomplish. It needs to leave the pier at 8:56 p.m. in order to be at the barge for 9 p.m. AI assistance. Although agent-based AI had its origins in robotics, many researchers quickly realized that the paradigm of agent-based AI had useful applications in the software world. There was no claim that this was general AI. The idea was that software agents could be built to do useful tasks on our behalf. Software agents operated in software environments, such as desktop computers and the Internet. The big idea was to have AI-powered software agents working alongside us as assistants on routine, everyday tasks like processing emails and surfing the web. The use of software agents in this way represented a completely different mode of human-computer interaction from what had come before. When we use an application like Microsoft Word or Internet Explorer, the application takes a passive, purely responsive role. These applications never take control or take the initiative. When Microsoft Word does something, it does it because you selected a menu item or clicked on a button. There is only one agent in the interaction between you and Microsoft Word, and that agent is you. The agent-based interface changed that. Instead of the computer passively waiting to be told what to do, an agent would take an active role in the same way that a human collaborator would. The agent would work with you as an assistant actively cooperating with you to do whatever it was that you wanted to do. By the mid-1990s, spurred on by the rapid expansion of the World Wide Web, interest in software agents grew rapidly. The title of a widely read article of the time, published by Belgian-born MIT Media Lab professor Patty Mass, captured the zeitgeist. Agents that reduce work and information overload. The article described a number of prototype agents developed in Patty's lab. Agents for email management, meeting scheduling, filtering news, and music recommendation. The email assistant, for example, would observe a user's behavior when receiving an email, read the email immediately, file it, immediately delete it, and so on. And, using a machine learning algorithm, would try to predict what the user would do when a new email arrived. When the agent was sufficiently confident in its predictions, then it would start to take the initiative and process the email according to its prediction. 2 decades would pass before agents became a practical reality, but they did. And there is a good chance that you use one every day. In 2010, an app called Siri was launched for the Apple iPhone. Siri had been developed at SRI International, the same institute that had developed Shaky 3 decades earlier. It was a direct descendant of the work on software agents from the 1990s and was envisaged as a software agent that users could interact with in natural language and that could carry out simple tasks on their behalf. Other mass-market software agents rapidly followed. Amazon's Alexa, Google's Assistant, and Microsoft's Cortana are all realizations of the same vision. They all trace their heritage to agent-based AI. They could not realistically have been built in the 1990s because the hardware available at the time was not up to the task. To make them viable, they needed the computer power that only became available on mobile devices in the second decade of this century. Acting rationally. The agent paradigm provided yet another way of thinking about AI. Building agents that can act effectively on our behalf. But this raised an intriguing question. The Turing test established the idea that the goal of AI was to produce behavior that was indistinguishable from that of humans. But if we want agents to act on our behalf and do the best for us, then whether they make the same choices that a human would make is irrelevant. Surely what we really want is for them to make good choices, the best choices possible. The goal of AI thus began to shift from building agents that make human choices to agents that make optimal choices. The theory of optimal decision-making that underpins most work in AI goes back to the 1940s and the work of John von Neumann, the same John von Neumann whom we met in Chapter 1, who did seminal work on the design of the earliest computers. Along with his colleague Oscar Morgenstern, he developed a mathematical theory of rational decision-making, which remains a cornerstone of economic theory to the present day. This theory showed how the problem of making a rational choice could be reduced to a mathematical calculation. In agent-based AI, the idea was that the agent would use their theory to make optimal decisions on your behalf. The starting point of their theory is your preferences. If your agent is to act on your behalf, then it needs to know what your wishes are. You then want the agent to act in order to bring about your preferred choices as best it can. So how do we give an agent our preferences? Suppose your agent has to choose between getting an apple, orange, or pear. If your agent is going to do its best for you, then it needs to know your desires with respect to these outcomes. For example, your preferences might be the following. Oranges are preferred to pears. Pears are preferred to apples. In this case, if your agent was given a choice between an apple and an orange and chose an orange, you'd be happy. If it gave you an apple, you would be disappointed. This is a simple example of a preference relation. Your preference relation describes how you rank every pair of alternative outcomes. Von Neumann and Morgenstern required preference relations to satisfy certain basic requirements of consistency. For example, suppose you claimed your preferences were as follows. Oranges are preferred to pears. pears are preferred to apples. Apples are preferred to oranges. Your preferences here are rather odd, because the fact that you prefer oranges to pears and pears to apples would lead me to conclude you preferred oranges above apples, which contradicts the last statement. Your preferences are therefore inconsistent. It would be impossible for an agent given such preferences to make a good decision for you. Their next step is to see that consistent preferences can be given a numeric representation, using what are called utilities. The basic idea of utilities is that each possible outcome is associated with a number. The larger the number, the more preferred the outcome. For example, we can capture the preferences in the first example by assigning the utility of an orange to be 3, the utility of a pear to be 2, and the utility of an apple to be 1. Since 3 is bigger than 2, and 2 is bigger than 1, these utilities correctly capture our first preference relation. Equally well, we could have chosen utilities so that oranges have value 10, pears have value 9, and apples have value 0. The magnitude of the values doesn't matter in this case. All that is important is the ordering of outcomes that is induced by the utility values. Crucially, it is only possible to represent preferences via numeric utility values if they satisfy the consistency constraints. See if you can assign numeric values to apples, oranges, and pears in order to represent the example with inconsistent preferences. The sole purpose of using utility values to represent preferences is that it reduces the problem of making the best choice to a mathematical calculation. Our agent chooses an action whose outcome maximizes utility on our behalf, which is the same as saying that it chooses an action in order to bring about our most preferred outcome. Problems like this are called optimization problems, and they have been extensively studied in mathematics. Unfortunately, most choices are trickier than this because they involve uncertainty. Settings of choice under uncertainty deal with scenarios where actions have multiple possible outcomes, and all we know about these outcomes is the probability that each will result. To understand what I mean by this, let's look at a scenario in which your agent has to make a choice between two options. To make this simple, I'm equating money and utility here. In practice, money and utility are often related, but they are not usually the same, and you will annoy a lot of economists if you assume that utility theory is simply concerned with money. In fact, utility theory is just a numeric way of capturing and computing with preferences. Here is the scenario. Option 1. A fair coin is tossed. If it comes up heads, your agent is given $4. If it comes up tails, your agent is given $3. Option 2. A fair coin is tossed. If it comes up heads, your agent is given $6. If it comes up tails, your agent is given nothing. Which option should your agent choose? I claim that option 1 is a better choice. But why exactly is it better? To understand why this is, we need a concept called expected utility. The expected utility of a scenario is the utility that would be received on average from that scenario. So consider option 1. The coin we are tossing is fair, not weighted to either heads or tails, and so we would expect heads and tails to come up on average an equal number of times. Heads half the time, tails half the time. So half the time, your agent would receive $4, and half the time it would receive $3. On average, therefore, the amount you would expect to earn from option 1 would therefore be 0.5 times $4 plus 0.5 times $3 equals $3.50. This is the expected utility of the option. Of course, if your agent chose option 1, then in practice, it would never actually receive $3.50. But if you had the opportunity to make this choice enough times, and you always chose option 1, then on average you would receive $3.50 each time you made the choice. Following the same reasoning, the expected utility of option 2 is 0.5 times $6 plus 0.5 times $0 equals $3. So, on average, choosing option 2 would give you $3. Now, the basic principle of rational choice in von Neumann and Morgenstern's theory says that a rational agent would make a choice maximizing expected utility. In this case, the choice that maximizes expected utility would be option 1, since this gives expected utility of $3.50 against the expected utility of $3 with option 2. Note that option 2 offers the tantalizing possibility of getting $6, which is more than would be received with any outcome associated with option 1. But this attractive possibility has to be weighed against the equally likely possibility of getting nothing in option 2, which is why the expected utility of option 1 is larger. The idea of maximizing expected utility is often grossly misunderstood. Some people find the idea of reducing human preferences and choices to a mathematical calculation distasteful. This distaste often arises from the mistaken belief that utilities are money, or that utility theory is in some sense selfish, since presumably an agent that maximizes expected utility must be acting only for itself. But utilities are nothing more than a numeric way of capturing preferences. Von Neumann and Morgenstern's theory is completely neutral with respect to what an individual's preferences are or should be. The theory copes equally well with the preferences of angels and devils. If all you care about is other people, then that's fine. If your altruism is captured in your preferences, utility theory will work for you just as well as it does for the most selfish person in the world. By the 1990s, the idea of AI as the paradigm of building agents that would act rationally on our behalf, with rationality defined according to the von Neumann and Morgenstern model, had become the new orthodoxy in AI, and remains so today. If there is any common theme that unites the various strands of contemporary AI, it is this. Inside almost all AI systems today, there is a numeric utility model, representing the preferences of the user, and the system will try to maximize expected utility according to this model, to act rationally on behalf of the user. Coping with uncertainty. One long-term problem in AI, which became much more crisply defined in the 1990s, was that of dealing with uncertainty. Any realistic AI system has to deal with uncertainty, and sometimes a lot of it. To pick an example, a driverless car obtains streams of data from its sensors, but sensors are not perfect. For example, there is always a chance that a rangefinder will simply be wrong when it says no obstacle. The information the rangefinder has is not useless, it has some value, but we can't just assume it is correct. So, how should we make use of it, taking into account the possibility of error? Many ad hoc schemes for dealing with uncertainty were invented and reinvented throughout the history of AI. But by the 1990s, one approach had come to dominate. The approach is called Bayesian inference. Bayesian inference was invented by an 18th-century British mathematician, the Reverend Thomas Bayes. He formulated a version of a technique that we now call Bayes' theorem in his honor. It is concerned with how we should rationally adjust our beliefs in the presence of new information. In the case of our driverless car example, the beliefs relate to whether there is an obstacle in front of us. The new information is the sensor data. Apart from anything else, Bayes' theorem is interesting because it highlights how poorly people cope with cognitive decisions involving uncertainty. To better understand this, consider the following scenario. The scenario is a pretty standard one invented long before the 2020 pandemic. A deadly new flu virus infects 1 in every 1,000 people. A test for the flu is developed, which is 99% accurate. On a whim, you take the test, and it comes out positive. How concerned should you be? After the test came back positive, I think it is a safe bet that most people would be extremely concerned. After all, the test is 99% accurate. So if I asked what the probability was that you had flu after the positive test, I suspect most people would say 0.99, corresponding to the accuracy of the test. In fact, this answer is hopelessly wrong. You would only have about a 1 in 10 chance of having the flu. So what is going on here? Imagine that we select 1,000 people at random and give them the flu test. We know that only about one person in this 1,000 will actually have the flu, so let's assume that in our test this is indeed the case. One person has the flu and 999 don't. First, let's consider the poor soul who has the flu. Since the test is 99% accurate, it will correctly identify someone who actually has the flu 99% of the time. So, we can expect this test to come out positive, with probability 0.99. Now, think about the lucky 999 souls who don't have the flu. Again, the test is 99% accurate, so it will only misdiagnose someone who doesn't have the flu about one time in every 100 tests. But we are testing 999 people who don't have the flu, so we can expect something like 9 or 10 of those tests to come back positive. In other words, about 9 or 10 of those people can be expected to test positive for the flu, even though they don't have it. So, if we test 1,000 people for the flu, we can expect about 10 or 11 of those tests to come back positive. But we can also expect that only one of the people who tests positive actually has the flu. In short, since so few people do have the flu, there will be far more false positives than true positives. This, incidentally, is one reason why doctors don't like to rely on a single test to make a diagnosis. Let's look at an example of how Bayesian reasoning can be used in robotics. Let's suppose we have a robot that is exploring some unknown territory, a distant planet, or a building that has been devastated by an earthquake. We want our robot to explore the new territory and construct a map of it. The robot can perceive its environment through its sensors, but there is a catch. The sensors are noisy. Thus, when the robot makes an observation and the sensors say there is an obstacle in this location, they may be right or they may be wrong. We don't know for sure. If our robot just assumes its sensor data is always correct, then at some point it will make a decision based on incorrect information and crash into an obstacle. Bayes' theorem here is used as follows. Just as in the test for flu, we can use the probability that the sensor reading is correct to update our beliefs that there is an obstacle at the relevant location. By making multiple observations, we can progressively refine our map of the environment, and over time, we become increasingly confident about where the obstacles are. Bayes' theorem is important because it gives us the right way of handling imperfect data. We neither discard the data nor accept it without question. Instead, we use it to update our probabilistic beliefs about how the world is. AI reaches maturity. By the end of the 1990s, the agent paradigm had become established as the orthodoxy in AI. We build agents and delegate our preferences to them. These agents act rationally on our behalf to carry them out, using rational decision-making as exemplified by von Neumann and Morgenstern's expected utility theory. And these agents rationally manage their beliefs about the world using Bayesian reasoning. This was not general AI, and it didn't give any roadmap for how to get to general AI. But by the end of the 1990s, the increasing acceptance of these tools led to an important change in the perception of AI within the AI community itself. For the first time, it really felt like we were not just groping in the dark, desperately clutching onto whatever we found. We had a well-established scientific basis for our field, one that was firmly grounded in respected and proven techniques from probability theory and the theory of rational decision-making. Two achievements in this period signalled the maturity of the discipline. The first made headlines around the world. The second, equally, if not more important, is unknown to all but AI insiders. The headline breakthrough was made by IBM, who, in 1997, were able to show that an AI system by the name of Deep Blue was able to beat Russian Grandmaster Garry Kasparov in the game of chess. Deep Blue took its first match from Kasparov in February 1996 in a 6-game tournament, but Kasparov won overall 4-2. An upgraded version of the system played Kasparov just over a year later, and this time Deep Blue defeated Kasparov overall. It seems Kasparov was very unhappy about it at the time, apparently suspecting IBM of cheating, but he has since enjoyed a good sideline to his brilliant chess career by speaking about the experience. From that point on, chess was, for all intents and purposes, a solved game. AI systems existed that could reliably beat all but the very best players. While you may well have heard of Deep Blue's victory over Kasparov, I think it is unlikely that you will have heard of the second major achievement of the time, although its ramifications are probably more profound. You may recall from Chapter 2 that certain computational problems are intrinsically hard, NP-complete to use the technical term, and that many problems of interest in AI fall into this category. By the early 1990s, it was beginning to be clear that progress on algorithms for NP-complete problems was such that this no longer represented the fundamental barrier that it had appeared 2 decades before. The first problem shown to be NP-complete was called SAT, short for satisfiability. This is the problem of checking whether simple logical expressions are consistent, whether there is any way they could be true. SAT is the most fundamental of all NP-complete problems. If you find an efficient way to solve SAT, then you have also found a way to solve all NP-complete problems. By the end of the 1990s, SAT solvers, programs to solve SAT problems, were sufficiently powerful that they began to be used on industrial-scale problems. At the time of writing, SAT solvers are so efficient that they are now routinely used throughout computing. They are just another tool that we call on when faced with NP-complete problems. This doesn't mean that NP-complete problems can now always be solved neatly. There will always be cases that bring even the best SAT solvers to their knees. But we are no longer afraid of NP-completeness, and this is one of the major unsung achievements of AI over the past 4 decades. For all its newfound respectability, not everyone was happy about what mainstream AI had become by the end of the 1990s. In July 2000, I was at a conference in Boston, watching a presentation by one of the bright young stars of the new AI. I was sitting next to a seasoned AI veteran, someone who had been in AI since the Golden Age, a contemporary of McCarthy and Minsky. He was contemptuous. "Is this what passes for AI nowadays?" he asked. "Where did the magic go?" And I could see where he was coming from. A career in AI now demanded a background not in philosophy or cognitive science or logic, but in probability, statistics, and economics. It doesn't seem as, well, poetic, does it? But the fact is, it worked. AI had changed direction again, but this time, the future seemed much more settled. Had I been writing this in the year 2000, I would have confidently predicted that this would be the future of AI for the rest of my career. There would be no more drama. We would use these tools, and that with them, progress would be slow but steady. I had no inkling that just around the corner, dramatic new developments were about to shake AI to its core once again.